So for the last couple of problems, we want to give you some context. So what we know, first of all, is that our initial function is going to be our starting function or our position function. Okay, in a business context, that's going to be revenue, your revenue function, your cost function, whatever. Okay, your first derivative is going to be your velocity function, which is also instantaneous rate of change. Which is also how your original function changes per item. Okay, so instead of saying how is the thing changing overall, if you take a derivative of a cost function, you're going to find out how is the cost changing at a specific item count. How is your revenue changing at a specific item count? Okay, so we'll just say marginal, okay, which means your specific count. Okay, your second derivative, which is going to be the derivative of your velocity function, is actually acceleration. Okay, so acceleration is going to tell you how your velocity is changing, or how is it changing when you find your marginal cost. Okay, how is that changing at that moment in time? So you're not just finding the marginal cost, you're finding out how it's changing. Okay, is it increasing, is it decreasing, whatever. All right, so in context, what we have is the acceleration of a falling object if during the construction of an office building, a hammer is accidentally dropped from a height of 1,296 feet. So that's over 100 stories. Okay, it's over 100 stories. The distance in feet that the hammer falls in t seconds is S equals 16 t squared. That is your position function. That's your position function. So this tells you how far it's going to fall. So my first question is, what is the hammer's velocity when it hits the ground? Well, remember, we're measuring this in terms of time. We are measuring this in terms of time. So I want to know what is my position at a certain time. So I need to know at 1,296 feet, how did I get there? Okay, how did I get there? So I'm going to divide both sides by 16. And then I'm going to take the square root of both sides. So the square root of 1296. My daughters took my calculator. I'm pretty bitter about it. All right, so the square root of 1296 over 16 is 9. Okay? So what you found is when you take, so this will give you 81, and then the square root of 81 is 9. Okay? What did you just find? For this thing to equal 1296, it's going to take 9 seconds. Either negative 9 seconds or positive 9 seconds. And we are in terms of time, so time is positive. Okay? So I know it will take 9 seconds for this thing to hit the ground. Okay? So that's going to be what's important. It will take 9 seconds. Now come back up here, and if my position function is 16 t squared, okay, then my first derivative is velocity. So my first derivative will tell me velocity, which is 32t. So remember, we're measuring in terms of time. Well, now I know when it hits the ground. So what is its velocity when it hits the ground? So I'm going to evaluate that at 9 seconds, because that's when it hits the ground. So now I have, hang on, go back to the normal thing. All right, so I've got 32 times 9. So 32 times 9 is 288 feet. So what you're measuring is that thing is falling at a rate of 288 feet per second. Okay, 288 feet per second. Now the last question says, what's its acceleration? So the acceleration is the second derivative of your position function, which is also the first derivative of your acceleration. Well, what's the derivative of 32t? It's just 32. There is no way to evaluate that. Okay, there's no variable. So you have a constant acceleration of 32 feet per second per second. Okay, and if you've had physics at all, you know that that's gravity. Okay, so since your hammer was not thrown, it was dropped. Gravity is the only thing affecting its acceleration. Okay, so its acceleration is 32 feet per second per second. So let's try it again. So we have the acceleration of a car. My position function is going to be negative t cubed plus 5t squared, and then plus 25t. And our context is the distance s in feet covered by a car t seconds after starting is given by the following function. And then I'm told that t is between 0 and 6. In other words, I care about from 0 seconds to 6 seconds. That's what I care about. Okay? So it says, please find a general expression for the car's acceleration at any time in this process. And so it flat out tells you, please find a second derivative. Well, I got to find a first derivative first. Okay? So my first derivative is going to be velocity. So I get a negative 3t squared plus a 10t plus 25. Okay? That's what I get. That's velocity. The derivative of velocity will give me acceleration. So my general expression for the car's acceleration at any time is given by my second derivative. So my second derivative is going to be a negative 6t plus 10. Okay? At what time does this thing begin to decelerate? Okay, so here's what you got to remember. Go back to basic math, okay? When does this thing decelerate? So your basic math is going to tell you to set this thing equal to 0, okay? In other words, this thing can increase in acceleration or this thing can decrease in acceleration. So when will it have an acceleration of 0? Because increasing will be a positive answer. Decreasing will be a negative answer. So I want to know, when does it hit 0? So think about it this way. If I've got a negative 6t plus 10, okay? So it looks like this. I want to know, when does it go from positive, okay, which means it's accelerating, and it changes to negative, which means it's decelerating. Okay, so don't look at the picture, look at where it is. Okay, so above means it's positive, below means it's negative. So above means it's accelerating, below means it's decelerating. So when does it hit this thing? That's what we're asking. So subtract 10 from both sides, and then divide both sides by negative 6. So I get a negative 10 over a negative 6, which is the same thing as 5/3, which is 1.6 repeating. Okay, so it's 1.7 seconds. At 1.7 seconds, okay, the change in velocity will be negative, okay, or will change, okay? So that is what that means, and that is section 3.5.